Welcome to Calculus 1, Chapter 1, Section 3. I'm going to look through this group of material using a homework assignment that I designed using WebAssign in conjunction with James Stewart's Calculus 8th edition Early Transcendentals. And the format of this video is going to be very similar to the couple of previous videos that we looked at. And we're just going to march through some example problems, and the example problems are going to be coming from this homework assignment that I designed. This is, the majority of the content in here would be considered review. This is information that you should know coming into a Calc 1 class, but it's very foundational to what we're going to be talking about later in the course, so let's make sure that we're up on this material. In this first problem, we want to start with some kind of a parent function, y equals f of x, and f of x could be something like x squared, or the absolute value of x, or the square root of x, or the cosine of x. But it's a parent function that has not yet been modified, and then in parts a, b, and so on, we're going to go through and modify that original function. Here we see that the modification is happening outside the function in part a, and you might generically see this represented as equaling f of x plus k. And so our k value, just by matching up pieces, the k you can see is a positive 9, and when a modification like this, using addition or subtraction, happens outside the function, it causes a vertical shift in the direction that you would expect. So in this case, plus 9 plus k, your k value is a positive 9, and that causes a vertical shift in the positive direction 9 units. Now in part B, we see the plus 9 happening inside the parentheses. And this might be presented as f of x minus h. And then if there were an additional modification on the outside, we'd have the plus k on the outside, but in this case we just have the minus h on the inside. So in order for x minus h to turn into x plus 9, the h value has to be a negative 9, so that it says x minus negative 9, double negative makes the positive. So our h value in this case is a negative 9. That h value represents a horizontal shift, not a stretch, but a shift. And since the h value is negative 9, which is the opposite of what it looks like it should be, right? This looks like it says positive 9, but it's really minus negative 9. And so we would shift in the horizontal direction and in the horizontal negative direction 9 units. So we're going left 9 units there. In part C, we've got a multiple happening. So there's a scalar multiple outside the function. And I like to think that modifications that happen outside the function have an impact that you would expect. So this is going to cause a vertical stretch by a multiple of 9. And if you think of, and you should, if you think of your f of x as being a y value, and it most certainly is, f of x was originally generating our y values, here we're taking our original y values, f of x, and multiplying them by 9. And what would happen if you took a y coordinate of a point and multiplied it by 9? If it's a positive y coordinate, it's going to get much higher. Vertically, it's going to move up. And if it were a negative y value, it would go much farther down on the graph. So this results in a vertical shift by a multiple or a factor of 9. A little bit more difficult to explain, but just realize that the multiple on the inside of a function here in part D, we're multiplying by 9, which is a number that's greater than 1, and the result is the opposite, so to speak, of what you might expect, which is going to be a horizontal shrink or a horizontal compression from both sides, right, from the right and from the left by a factor of 9. You can think of that as if you were looking at a graph and then you applied this multiple of 9, you would need to take all of the x coordinates of all of the points on the graph and divide them by 9. And so all of your x coordinates would get closer to the y-axis as we compress it in from the left and from the right. In part E, we have a couple of modifications. The -1 at the end of this statement does what we already talked about, so that's going to cause a vertical shift. I'll leave you to determine which direction it goes. But the negative in front of the function is the same thing, or is equivalent to multiplication by -1. And remember that that f of x that you see there represents the original y values of the parent function. And we're taking these original y values and multiplying them by -1. So if you had a point that was above the x-axis, because it had a positive y value, you multiply it by -1, that point now has a negative y value. It gets flipped over the x-axis, which is why these multiple choice options you're seeing say reflect the graph about the, and then you have to choose x or y. And in this case, since we're taking the opposite of our y values, it's going to cause a reflection over the x-axis. Anything that was above the x-axis gets folded over and now exists below the x-axis. Anything that was below now appears above. For those of you who don't actually have access to this homework assignment, we'll put that whole thing on the screen for you to check it out. In part F, again, we've got a couple of modifications. The 9 that's on the outside of the function, we talked about what kind of a result that has. On the inside of the function, the actual x variable is being multiplied by a number, a scalar. And again, when there's a modification inside of our function, it has sort of an opposite effect of what you might think. This is the 1/9 in part F is going to cause a horizontal stretch or shrink. And you might think that the 1/9 is going to make your graph 1/9 as wide as it used to be. In other words, horizontally shrinking it or compressing it. But in fact, that is backwards from how we need to actually think of it, or what actually happens, and our graph would get 9 times wider. So a horizontal stretch by a factor of 9 as a result of that 1/9. So I'm kind of cruising through these. I'm not being super comprehensive on all of them. I'm assuming that you're listening to the initial conversation about the first question, and then if you have to go back and read something about part A, then so be it, and apply it forward to part F, or whatever other part it is that we're currently talking about. Here's a graphical question. The graph of y equals f of x is given, and we can see it in blue there. And that doesn't look like any parent function that I'm familiar with. So this is sort of a random looking parent function, and we have to use the different transformations that we were just talking about in order to modify this parent function. So for example, part A has a -4 inside the parentheses, so inside the function, and that -4 causes a horizontal shift. And because it's inside the parentheses, it's going to go, you might want to think of it as the opposite of what you would normally think. It's sort of counterintuitive. So the -4 is actually saying x minus +4. So the h value, so to speak, inside the parentheses here is a +4. So that would cause a horizontal shift of 4 units in the positive direction. Let's look at the way that this question is phrased again. Okay, so now we need to match that up. And as a result of taking the parent function and horizontally shifting it to the right 4 units, we look back up at the graph, And if we took our blue curve and we shifted it to the right 4 units, which one of those graphs would we end up with? Taking our blue graph, shifting it to the right 4 units, looks to me like we end up with graph number 3. And so we would come down here and choose 3 as the correct option. I'm not going to go through the rest of these because we did just talk about transformations, and I'm going to leave it to you to apply them visually, to answer visually by looking at those other graphical options instead of answering using words like we did in part 1, like horizontally shift 4 units in the positive direction and so on. But here the plus 3, we saw an example like that in part 1 or number 1. Here is a constant multiple on the outside of the function, only a little bit different than what we talked about already, because this multiple is a 1/3. And remember that f of x was originally generating y values. You take an x value, plug it in, you get out a y value. Except here, before we assign that y value to our new y coordinate, we're going to take that original y value and multiply it by 1/3. So all of our y values are only going to be 1/3 of what they used to be. And visually, graphically, this is actually an interesting one to look at. Let's just look at maybe one component of that. On the original parent function, I need a different color pen here. Let's see if green will show up fairly well. Yeah, that looks pretty good. Make it a little more visible. Nice. Okay, so looking at the blue curve on our graph, I'm just going to grab a random point, somewhat random. I'm going to pick the point at the top of the curve here. And remember that part C that we were just looking at said that we should take our original y values generated by f of x and multiply them by 1/3. So what's the y coordinate right at the top of this blue curve? I would say that point has a y value of 3. And if you take the 3 and multiply it by 1/3, you get a new y value of 3 times 1/3 is 1. So now I'm looking for one of these sort of magenta curves, 1, 2, 3, 4, or 5, and asking myself, well, which one of those contains a point with a y coordinate of 1? And some of you are thinking, seriously, why are you dragging this out? Obviously, it's number 4. This point clearly has a y coordinate of positive 1. These graphs are going to get more complex, but the process, the thought process that we're going through remains the same. Doesn't matter how complicated the graph looks like, or how complicated the graph looks. So we can apply that in order to choose our correct answer for part C. Part D, remember that this causes a a flip or a vertical reflection over the x-axis. Anything that was above is now below, anything previously below is now above, and we need to apply this transformation. Be careful, that plus 4 is inside your parentheses. It's going to cause a horizontal shift. I'm going to leave it to you to decide which direction it gets shifted. Same thing with the plus 6. Be careful. Make sure you shift the parent function in the correct direction, and then take the y values from that original parent function and double them. So be careful as you're going through these transformations that require 2 steps. In part 3, we move from transformations of functions. And transformations of functions is the horizontal shift, vertical shift, horizontal stretching or shrinking. Sometimes we call it maybe compressing the function, vertically flipping the function. The one that we didn't look at in the first 2 problems, let me just slide up here so I can give you a note in case you see it. If we had worked with a function that said y equals f of negative x, the negative inside the function would have caused a reflection over the y-axis. Anything to the left of the y-axis would have flipped over to be to the right of the y-axis, and vice versa. So that is a horizontal reflection. In part 3, we're looking at function composition. Some of us have heard of this referred to as fog notation for obvious reasons. Functions are not always named f and g. There are functions that are called p for position. S as in Sam, is often the name of a function that we see referring to position. V for velocity. A for acceleration. We're going to see all three of those later. And just a quick reminder on function composition or fog notation. Another way that f of g can be written is, well, let's stay with green. Here we go. We could also write this as that way. This reads more like f of g of x. And the way that I prefer to think of it, and sometimes I even write it out this way, is like this. This makes it very clear to me. You'll notice that the f and the g are occurring in the same order from left to right. This makes it really clear to me that the g function is getting plugged into or substituted into the f function. If I were working with these same two functions and the request was for f of 2, what would I do with the number 2? I would certainly take it and plug it in place of x, because this x had been changed into a 2. If I change the first x into a 2, I change all of them into a 2. However, here we're not plugging in a 2 into our function, we're plugging in g of x. And so I will replace the x's in my original f of x function. I'm going to replace those x's, or that x, with g of x. So we will need to take g of x instead of the number 2 and square it, and then subtract 1. Simple substitution. Okay, if you do too many steps at once, it's liable to be confusing. We're just going slowly here to have a good reminder, make sure we know how to do this. Now I'm going to replace this g of x with what g of x actually is, which is, and notice it's still in parentheses. I put these parentheses around the g of x. I recommend that you do that, because the next thing we're going to do is replace g of x with 4x plus 4. You'll see that the 4x plus 4 is in parentheses, just like the g of x was. We'll put the square on the outside of there. Don't forget the minus 1 at the end. And from there, you need to FOIL carefully and combine like terms. And foiling, you might be the kind of person who would benefit from writing it out like this. Right, because squaring something means multiplying it by itself, and if the foiling process is going to be more accurate for you, if you write it out like this, make sure you do that. Okay, I'm going to leave you to do the foiling and combining of like terms, and then I want to go down and talk about the domain of this function. Now that you've foiled it out, what you're looking at is a statement that starts with 16x squared, and then there's a term that has an x to the first power in it. And then at the end, it looks like you've got maybe a plus 15, okay? That's called a polynomial. Your x variable is only being raised to powers, or your x variable only has exponents that are positive integers. X to the second power, x to the first power. And then the constant term, the plus 15, is really x to the 0 power. Okay, so they're non-negative integers. Anyway, that's a polynomial. And you should know, as a Calc 1 student, that polynomials have a domain that consists of all real numbers. All right, you can plug anything you want into a polynomial. There's no danger of division by 0. There's no danger of square rooting a negative number. So our domain for this function, using interval notation, will go from negative to positive infinity. Don't forget that in interval notation, infinity and negative infinity are always accompanied by a parenthesis and never a square bracket. G of f is the next part of this question. We have to take our g function, we have to take our f function and plug it into the g function. I'm going to rewrite this using my favorite notation, g of f of x, and I'm going to leave it to you to sort of mimic the process we did with part A, being very careful and plugging your f function into your g function. And I am a big fan, and you'll see me do this periodically, of thinking about this process or reminding myself, how do I do this correctly again? How do I plug a function or an expression into another function? Remind yourself the process by plugging in a 3. What would it look like to take the number 3 and plug it into my g of x function? Well, if this x becomes a 3, then this x needs to become a 3, except in part B, we're not plugging in a 3, we're plugging in an f of x. So use your notation, stay organized, sharp pencil, lots of paper. The domain of that function, remember, if it turns out to be another polynomial, your domain will go from negative to positive infinity. If it turns out that you have to square root something, or if you end up with a variable in a denominator, then you have to start being more careful. F of f, g of g, here you're plugging the function into itself, first with f, then with g. Find each of the following functions. Here's a great example of, remember earlier I was saying, even if the graphs look more complicated, the process of doing those transformations is the same. This is a great example. Now our g function is a trig function. Don't freak out. The process of building the composite function, taking g and plugging it into f, is the same as in the problem that we just did. Let's write it out using this other format, f of g of x, which is f of cosine of x, which is 2 minus 3 times, what's our input value? It's not a number, this time it's an expression, cosine of x. So this is the new function that we're looking at, 2 minus 3 cosine x, and the subsequent question is to state the domain of the function. Well, as we're choosing x values that we may or may not be able to plug into this function, is the 2 going to mess us up at all? Are there any restrictions imposed by the 2? I don't think so. The thing you really need to be looking at here is the cosine function. Are there any restrictions on the cosine function? If you're in Calc 1, you should know the answer to this question because you should have been through a pre-calc class, which should have been heavy on trigonometry. Remember, the graph of the cosine function looks like a wave, and how far to the left and to the right does that wavy line go? Can you picture it? It goes forever to the left and forever to the right. Nice wavy line, and it doesn't have any asymptotes or any holes in it or anything like that, so the domain for the cosine function does go from negative to positive infinity. Now the range would be a different story. As that cosine wave goes along, it only reaches a maximum height of positive 1 and a lowest y value, minimum you could say, of negative 1. And then we would have to apply this value of negative 3 because that's going to cause a vertical flip or reflection and a multiple of 3. So that would be a vertical stretch. So all of a sudden your range would not go from negative 1 to positive 1, it would go from negative 3 to positive 3. And then the 2 that's out there would cause a horizontal shift, sliding our graph to the right 2 units, not impacting the domain and also not impacting the range. G of f. This one's interesting. We'll take the cosine function. And as an input value, we're going to plug 2 minus 3x into the cosine function. as we take x values and plug them into this function, is it possible that we could end up creating a number that the cosine function is incapable of processing? Can I take a number and plug it into here such that when I multiply it by 3 and then negate it and then add 2 to it, can I end up with a number in here that the cosine function can't handle? Well, what numbers can the cosine function handle as input values? We just said anything from negative to positive infinity. So there are still no restrictions on this composite function, because no matter what we're tripling or negating or adding 2 to, the cosine function is going to be able to process it. So your domain is still all real numbers. The domain of the next function, f of f, I'm going to leave you to do that on your own. And then here's g of g, which is g of x. And that is the cosine of x. When I plug x into the inner part of this function, will this cosine function be able to handle anything you throw at it? The answer is yes. The domain is from negative to positive infinity for cosine. What are the output values of the cosine function? Just the basic cosine function. What are the output values? What's the range of the cosine function? Alright, not my best work. However, this is the basic cosine graph. This curve does continue all the way to the right, all the way to the left, forever. And remember that its maximum value is positive 1, its minimum value is negative 1, so this curve over here should have come down lower. Inclusive, including negative and positive 1. So this cosine function is going to output numbers between negative 1 and positive 1. Do you think that this outer cosine function will be able to handle the negative 1 through positive 1 numbers that it has to process? I would say, because the cosine function has a domain of all real numbers. So there end up being no restrictions on g of g either. Negative to positive infinity it is. Here you've got f of g of h, f of g of h. So we're taking the h function first, 3 parentheses, yep, that's it. We're going to take the h function and plug it into the g function first. And then whatever we get from building that, we'll take it and plug it into this x as an input value in our f function. And if it were appropriate to distribute multiplication by 9, you could do that. If it doesn't look appropriate, if it doesn't look like you're supposed to be able to distribute by 9, don't force it. Don't do it. And then don't forget that minus 5. Here's another composite of 3 functions. H is going to go into G, so you're going to have to take this and plug it into here and square it. Should you square it right away? Should you start foiling right away? Maybe, maybe not, because once you finish building that composite function, you have to take it and plug it into here. And maybe when you do that, the minus 1 will turn the inside of this radical, the radicand, the stuff under the square root symbol, maybe the stuff that you end up with under there will be square rootable. Maybe it'll be a perfect square. I'm going to leave you to examine that. I would be impressed if it did turn out to be a perfect square, because you're already taking x to the third plus h and squaring it. The result of that would be a perfect square for sure. But then you're going to subtract 1 from it. That'd be pretty cool if it still turned out to be a perfect square. Think of a perfect square, like 9. If you subtract 1 from it, does it turn into a perfect square? It does not. Can you think of a perfect square that if you subtract 1 from it, you get another perfect square? 81 minus 1 is 80. Not a perfect square. Should I keep looking at larger numbers? Should I keep looking at smaller numbers? Interesting. I'd be interested to hear if you can come up with a number that if you subtract 1 from it, still ends you up with a perfect square. I'm thinking of one that's a contender. I'll let you think on it though. Express the function in the form f of g. So we're still doing function composition, but we're sort of doing function decomposition now. Does this capital F function look like two functions where one has been put into the other? In cases like this, in questions like this, I always look for parentheses to guide me. Are there parentheses that are sort of bundling part of this statement together? There are. These parentheses, if my pen will work, these parentheses right here are sort of grouping the 5x plus x squared together. And then on the outside, is there another action that's being taken? Yes, there is. It's the exponent of 4. All right, so now I have to decide if indeed the 5x plus x squared is one of my functions and raising to the 4th power is another one of my functions. Which one is lowercase f and which one is lowercase g? Well, we're trying to express this function in the form of f of g, which I like to write as f of g of x. And when I write it this way, it's way more clear to me which one is the inner function and which one inner function and outer function. Sorry, I thought I just muted the mic. So what do you think? You're looking at it. F of g of x, which one's the inner, f or g? I'm going with g as the inner function. And since this expression is inside the parentheses, I'm going to call that my g function. So g of x will equal 5x plus x squared. And this one, well, I'm not going to do all the work for you. If this is our function f of x, how should I write that so that it ends up applying a power of 4 to whatever I put in as an input value? And remember, what is it that I might end up putting in as an input value for x? Could put in a number, or I might end up putting in an expression. So when I take g of x and I put it into that function, I need to end up with 5x plus x squared to the 4th power. So your challenge is to figure out how to represent f of x. And we're back to some graphical representations here. This is question number 8. We're given here graphs of f and g, and we want to evaluate f of g of 2. And there are a handful of these questions, or more than a handful. So let's just look at one, and then I'm going to leave you to replicate that thought process and answer the rest of these questions. The first thing I would ask myself is, what is g of 2? The 2 that you're seeing there is an input value, which is typically an x value. So I'm looking at my g function, which is the blue one, the upper of those two graphs, and I want to find the point on the blue graph that has an x coordinate of 2. That looks like it's this point up here. It's the maximum, as a matter of fact. It's the highest point on that curve. And what is the corresponding y value to that point? 2 comma what? 2, 4, 5, I think it's 5. So I'm going to say that this f of g of 2 is equivalent to f of 5. 2, 5 was that point up there. G of 2 actually represents a y value. 2 is the x value. So now I've got f of 5. Now I need to look at the magenta graph, the lower of the two, and find a point on that curve. Even though it's made of straight lines, often we still call it a curve. I need to find the point on that curve or on that graph that has an x-coordinate of 5. So I'm looking down at my graph here, 2, 3, 4, 5. Ooh, hello. I set my hand down on the screen and it took off. All right, let's try that again. 2, 3, 4, 5. Okay, so I'm here at 5. Now I need to go up to my graph, and it looks like we're looking at this point right here. And what's the y-coordinate of that point? Well, if the y-coordinate of this point was 5, safe to say we came down 1. That has a y-coordinate of 4, which means that f of 5 is 4. So our final answer for part A in this question would be 4. See if you can go through that same process for the rest of these questions. If it's helpful to you, rewrite this notation, fog notation, rewrite it as f of g of 0 so that you can mimic the process that I just did in part A. Don't worry about if it's a composite function where it's composed with itself. This can still be written as g of negative 2, and you can use the same thought process that I talked through in part A in order to answer part E. Just because it's the same function being written twice, don't let that throw you. Keep applying the same method to get your solution. I think we only have a couple of questions left. This one's number 9. A stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 35 centimeters per second. Express the radius of this circle as a function of the time t in seconds. Express the radius as a function of time. Well, when a stone's dropped into a lake, I can imagine that as soon as the stone hits the lake, I can imagine the stone like the sun setting into the ocean. It's halfway into the ocean, no ripples yet. But a second later, you can bet there are going to be some ripples radiating outward in a circular pattern at a speed of 35 centimeters per second. So after 1 second, right, if the stone gets dropped into the water here, 1 second later, the ripples will have radiated outward. And after 1 second, how far away from the stone do you think the ripples will be if the ripples are traveling at 35 centimeters per second? After 1 second, I would say 35 centimeters. And after 2 seconds, how far away would the ripples be? 35 there and 35 there. Now we've got 2 35s, which makes 70. I'd be willing to bet that the radius of that circle is equal to 35 centimeters per second times the number of seconds, which is not s. We're using the variable t, 35t. And the area of the circle as a function of the radius. We all know that the area of a circle is represented by pi r squared. Do we know what the radius of the circle is? Well, it depends on how many seconds have gone by since we dropped the stone into the water. So our area function, just organize this a little. The area can be determined by taking the radius and plugging it into the area function. I'm telling you that this over here is the area function, and you know what your radius function is. It's up here behind my head. There it is, top left of your screen. There's your radius function. So I'm giving you the radius function and the area function, and you need to build the resulting function and write your solution in here. I think that you can handle taking r of t and plugging it into our function a. I put this little circle down here just because we're talking about the area of a circle. If it were a square, I would have drawn a little box. Interpret the answer you found in part B. I don't want to read all of those into the microphone. I will let you read those and see if you can make a good selection there. And question number 10. The graph of a function is given. Use it to graph the following functions. So this is the graph of f, and here inside the function, instead of an x, we have a 2x, and remember that the multiplier inside the function has a counterintuitive impact on the graph. So this will not make our graph twice as wide. It will actually make it half as wide. And you can make that happen. You can facilitate that graphically. In order to make your function half as wide, take all of the x coordinates of all of the points and cut them in half. So I will do one of these with you. The x coordinate, let's start down here. The x coordinate here is 0. What's half of 0? 0. So we're going to have a new point that's still going to be there. I didn't change the y value. The 2 that's inside this function is not impacting y values. It's going to cause a horizontal stretch or shrink, in this case a horizontal shrink, so that's only modifying x values. If I look at this point up here, the maximum, the x coordinate there is 4, half of 4 is 2, so we'll have a new point here. And then maybe I'll come all the way down to this minimum point here, since there's a straight line connecting those points. That point down there has an x coordinate of 4, 8, 16. Let's half that. So it's going to become 8. So this point's going to move over to here. And if you want to draw some little arrows, you could, I suppose. This point's moving over to here. This point is moving over to here. And this point way out here to the right, what's the x coordinate there? 4 once, twice, 3, 4, 5, 6 4s makes 24. Half of that is 3 4s. 1, 2, 3. So we're going out to 12. So this point is moving over to here. And then if we needed to draw the graph by hand, excuse me, we would simply connect the dots, in this case with straight lines. And sketching that is not a bad idea, and then go down into your multiple choice options and see if you can pick the correct one. We need to start at 8, 2. This one has an 8, 2 on it. Or sorry, 2, 8. I misspoke. And then what was the next point that we had? Up there by my head, this lowest point has coordinates 8, -4. So let's go back to option number 2 here. 8, -4. Yeah, this one's looking good. And then lastly, we're at 12, 0. And yeah, that was the last point that we graphed on our graph. So it's looking like this graph is the correct answer. It doesn't matter if this parent function that we were given, which is some arbitrary weird function, it doesn't matter if that has straight lines in it, if it has curves in it, if it's a recognizable trig function, if it's the cotangent function with asymptotes. The process is the same. When you're modifying inside the function with the 2, that causes a horizontal shrink, which is facilitated by halving or dividing all of your x coordinates by 2. Keep all the points on your original graph, keep the y coordinates the same, and just half the y values. Draw yourself a somewhat accurate sketch, and then match that up to your multiple choice options. Let's see, was there another question after this? Just more multiple choice options, more functions being modified. Oh good, here's a problem you get to work on where the x inside the function has been negated. Remember that that causes a negating of all of your x coordinates. Any x coordinates that were positive become negative, and negative become positive. It causes a flip or a reflection over the y-axis. Here's a double reflection. You're going to take the parent function, flip it over the x-axis, and flip it over the y-axis. And that is it for that series of questions. 45 minutes of function composition and function transformation. That ought to bring you back up to speed. If not, don't forget that whatever book you're using, you should be able to dip in and look at some additional examples, and hopefully maybe some mini lectures provided by your author and publishing company. Hopefully these examples were helpful, and I will see you in the next section. Thanks.